Okay, in this video what I'll do is I'll give some idea of the laser diode operating characteristics. When we talked about the LED, we had a very simple type of behavior for the LED where our response function was basically just linear up to some threshold like this, where we had drive current versus optical power out. So what we'll do is we'll basically draw the same diagram for the case of the laser diode, and we'll see that it's more complicated basically. And so there is a linear region, but we have to reach a threshold before we hit that linear region. So the output power, optical power curve characteristic so we have P optical and we have drive current here. Starting with 0, basically what happens is you have to take the drive current all the way up to some threshold before you start getting the output, and basically this brings your gain medium up to its threshold. Okay, so we had that gain medium, and by injecting our current into it, what we're doing is we're creating more and more photons. Finally we get enough photons that we can have spontaneous emission. So we have our threshold. So this is our current, our drive current threshold. Okay, and then once we reach that drive current, then we can go ahead and operate over some over some range of output powers. Ultimately though we're going to saturate again. You can't drive the thing forever with some maximum power. Okay, and so here's where we want to operate though. Here's where we're going to operating region. Okay, so we're going to operate along that part of the curve. And basically, we can write down a lot of the same equations for optical power and drive current, much like we did for LEDs. Something like this, where we talk about driving with a sinusoidal drive current and the resulting optical power out. But the whole thing is offset by this drive current threshold. Okay, so the equations are more complicated, and we don't really have to worry about them too much. Basically, what you should know though is that we do have a drive current threshold, and that's associated with the threshold in the gain medium. Okay. The other thing to know about the optical power characteristic is that this drive current is induced by a voltage that we put across. I drew the electrodes. Basically what we're going to do is we're going to put electrodes across this multiple heterojunction structure, and we're going to get a voltage across here, and that's going to induce a current, that drive current. It takes just a volt or two typically in our structures to create drive currents on the order of a few hundred milliamps. Okay, and then that way we're going to get optical output powers of typically 1 to 10 milliwatts. So voltage, applied voltage, is typically 1 to 2 volts. Drive current is typically in the range of 100 milliamps. And finally, optical power out is in the range of say 1 to 10 milliwatts of optical power out. So that gives you some idea. The other thing that makes laser diodes more of an issue in dealing with is the fact that this whole curve is temperature dependent. So we have our drive current versus optical power out, and basically what I'll do is sort of reproduce figure 6.25 here. We're going to have, you know, some sort of a threshold for a high temperature, okay, and then as we lower the temperature we're going to get a whole series of curves like this, okay. And T lower, okay, and so the whole thing sort of depends on temperature. The way that this operates depends on temperature, and of course the amount of drive current going through it changes its temperature, so the whole device heats up. It gets to be kind of complicated. In any case, we can make these things and we can drive them, and they're very reliable. The other thing that we do with these lasers that we use for telecom applications, what we want is to get a single longitudinal mode, okay, single longitudinal mode. And that's going to give us the narrowest possible delta lambda. And we know that the narrowest possible delta lambda, that is the narrowest spectral width of the source, is going to give us the largest bandwidth distance product because of dispersion. And so instead of having something that looks, a gain curve that looks like this in frequency, where we go like this and we get an output of our laser that includes several longitudinal modes. These are the cavity modes. Now what we want is to have only one of those really resonating. So we have all of these in here, and we're going to try to pick out just one. And we can do that by various tricks. Let's see, what do we use to do that? What we use to do that, generally speaking, is to vary the mirrors that are used, okay, on the sides, so that they only resonate and they only become very good mirrors at one of these wavelengths. And we do that effectively in what's called a distributed feedback laser diode. Okay, so we give some sort of a structure so that only that one longitudinal mode will actually propagate within the structure. Okay, so we essentially put a grating over top of it. You can think of it as making it so that the mirrors themselves are only reflecting it at one of those wavelengths. Okay, and so these are called SLM lasers, single longitudinal mode or single mode lasers. Okay, and they're much more preferred. We're always trying to get a single mode laser out of our structures to give us the highest bandwidth, and generally speaking, that is the type of laser that we'll use in our telecom systems, is single mode lasers. We can also make them tunable through various tricks, and that's nice for WDM systems. We won't get into any of the details on how all of that works though here, but we can make tunable laser diodes. Okay, I'll stop here. Thanks.